Kudos. Yeah. So, can you hear me? So here's a scheme of things that I'm going through. I'll just like briefly touch upon yesterday's stuff. That's like the recap of the classical VI framework. Then I'll reframe inference as a stochastic observation problem. I'll have like a very short mini tutorial on automatic differentiation, just to know like what's going on. Generally, when you use some software, like there's lots of terms thrown in for more to get an idea. Then the main thing, that how do you kind of pose or estimate Monte Carlo gradients. And once you have these two ingredients, you have a good automatic differential software, you have Monte Carlo gradients, then basically you come up with the algorithm that for the automatic differentiation variation inference. And this algorithm generalizes, so you have very little restrictions in terms of like what type of approximation, what type of models. And then finally, there are some practicals. So that's it. So, yeah, it was what?
Click on the slides with the mouse.
Okay. Okay, so the classical variation inference. Before we go there, just like general like description of a like most common probabilistic models that we always have. We have some global parameters or variable theta, and we have some local parameters that changes with like data, so they are linked with the data. And the general goal is to kind of approximate the posterior using a tractable distribution, which we call the variational approximation, which are parameterized by some parameters that we have to find out. So that's the basic variational inference setup. And generally, as and then went through yesterday, that we start with like minimization of the KL divergence. There are many other divergence or distances between densities that we can choose, and throughout this masterclass, there will be a broader introduction to those sort of divergence measures. But generally, if we want to minimize the KL, we generally do not directly do that. Instead, we use something called elbow, which is bound to the marginal likelihood. So basically, what elbow does is like, if you frame it in this way, like it kind of gets you the expectation of the log joint. So you can think in terms of like the Q tries to place its mass on the map, but then you're penalizing that thing with so that the Q has more diffused sort of density. So that's one interpretation. The other interpretation is like, obviously, if you frame it in terms of that, where you have on the left-hand side is, on the past term is your expectation of the likelihood. So you can think of like Q is trying to place all its mass near the MLE, but then obviously you are penalizing with the KL divergence. I mean, like,
sorry, I missed what lambda was.
Lambda is the variational parameter.
Oh, yeah, okay. What was beta yesterday?
Yeah, but I'm using lambda. And so, yeah, so Q tries to puts its mass at the MLE, and then you're trying to penalize the KL divergence between Q and the prior so that you have more diffused density. So basically, the classical VI works with what we call the mean field variational inference, where we take the variational distribution and we use sort of a factorized form. And the main idea is that generally for this classical mean field variational inference, you need conjugate models and belonging to the exponential family. So if you have your densities belonging to the exponential family, you can basically, if you can do Gibbs sampling, then you can basically write down the complete conditional. And the main trick here is to choose the variational distribution in the same family. So this is how you generally kind of do it in classical framework. So you take the complete conditional, you then kind of choose your variational distribution in the same family. And then basically it boils down to just the coordinate ascent or variational inference or CAVI, where you just iteratively update your variational parameters, you update your global parameters, and you update your local parameters. And these all these derivation and these things yesterday session, these were covered. But the main thing to see here or note here is that if you have a very large number of data points, firstly, then obviously you have to loop through all these data points. So that means you can't scale it to massive data set. So basically, the whole point of doing variational inference was so that, well, we can do things faster. But because of that, each data point loop, we are stuck. So that's the first problem. Okay. Now, obviously, there's some things we need to think about. That's like when VI was introduced in machine learning, it was late 90s. That time, actually, MCMC software sucked. So we had pathetic MCMC. So in fact, we had pathetic hardware to begin with. From 98 to 2022, actually, there has been sea change in software and mainly hardware, actually. In fact, I would say more hardware. And so that's why we now have very fast MCMC software, right? So actually, we can use MCMC for relatively large data set. And then a lot of the people here in this masterclass, they are working on scaling up MCMC for big data set. So that the first point is important, but there are a lot of people working on that. The second point is a killer point, because as I was discussing this morning and yesterday, that as soon as you have non-conjugate models, then you can take this expectation and that's it, end of story. So that's where the things were. There were some work earlier, but basically this is the main problem, that you cannot use non-conjugate models. And the solution to both these problems is based on stochastic optimization. And this solution is obviously motivated from the resurgence in deep learning back in 2010s. And so people kind of borrowed those ideas into probabilistic modeling, or I would say Bayesian statistics. So how do we pose VI as a stochastic optimization problem? So let's say that we can take the expectations. If we can take the expectations, then we can think of it as like a gradient descent problem, where we simply apply gradient descent to optimize the parameters. Now, obviously, we cannot take expectations because there are issues. But if we can take like unbiased estimates of the expectation of the gradients, then there is the classic stochastic optimization framework invented back in, you can see, 70 years back. And that gives you something we know as stochastic gradient descent. So you just, rather than using the exact gradients, you use a Monte Carlo expectation. So that's basically the framework. So that, I mean, like the entire modern variational framework is lying on this, or standing on this thing, is that you cannot take the gradients, you take an unbiased estimate. So I'll come back to this, but the other thing is, obviously, since we want to scale variational inference to really complex models, then obviously we don't want to take gradients by hand. And one of the big impetus in like variational inference becoming quite mainstream these days is automatic differentiation. So I'll talk a bit about automatic differentiation first. So consider like we have a function from an n-dimensional input space going to m-dimensional output space. And what we want to do is calculate the Jacobian, right? And now think of this function as a composite function. So obviously, just apply chain rule. You can apply chain rule to kind of calculate the Jacobian. Now, obviously, if you have many layers of functions, so you can think of like chaining composition, like we have one after other functions, then you can obviously chain the Jacobians. And so the whole job of automatic differentiation is to, when you have this sort of composite function, like composition of L functions, then you want to do two things. First is you kind of want to find what is called the Jacobian vector product. That's like you have a vector in input space and you want to find the oops. Okay. Oh, that's all right. Okay. So we want to do two things. First is we want to find like action of the Jacobian on a vector in the input space. So like easy way to think of this is like taking a directional derivative basically. So you have like a tangent vector U. You want to take like the action of the Jacobian on the tangent vector. And then that's basically known as forward mode automatic differentiation, or doing things in the forward mode. And in the reverse mode, what you're interested in basically you have a vector on the output space, and then you want to take the action of the Jacobian on that vector. So you can think of that like a cotangent vector. So depending upon what you want to do, basically you have two modes of the differentiation operation. And in both modes, you can actually calculate the Jacobian of this sort of composite function using a kind of applying the chain rule in slightly different. Oops. Yeah. Okay, so let's go to an example. Okay, so you have this function, right? Composition. So in a forward mode thing or a forward mode AD, what do you want to do is basically first we want to write down it as a computational graph. Then we want to do exactly what we do in like normal high school, like applying chain rule. We want to just expand. And basically we are just differentiating the inner function and we are expanding. What happens here is that you can see that you can simultaneously evaluate the computational graph. That is like you can populate the graph with values. At the same time, you can also populate your derivatives. So the thing to note here is that you can evaluate both these things simultaneously. So basically, what happens is like this: you have this sort of recursion where you apply your tangent vector to your first function Jacobians, and then you kind of push it from left to right, and you end up with this sort of recursive relation. Now, why it's useful in the sense, if you notice this first term or the second term, is that you actually do not need to form the matrix. So you can do this analytically. So you write your computer code in such a way that it calculates your actual function value, that is the intermediate graph output. So for example, your first function is h, you write a code to calculate 8, but simultaneously you can also because you know the function, you can write its action, its Jacobian times whatever it's coming in its input analytically. So you do not need to form these matrices, and you can actually, once you build a library of functions, like let's think of transcendental function or some like basic elementary of functions, with calculating its output as well as calculating the action of its Jacobian on its input. So obviously that way you can sequentially evaluate your Jacobian, and you can evaluate your Jacobian vector products without forming the matrix. So let's just walk through an example more clearly. So consider the following function, right? It's iPhone.
Also, did we get a pop-up? with the requesting to insert the code. Well, if anyone sees a pop-up in requesting.
Yeah.
I'm just gonna get into the call and do it from here.
Okay.
I was gonna say that, yeah. We'll make
I
some
don't know if you can do it without being the.
Co-host.
Maybe you can make a host. Yeah, no, it's fine.
How do I do? Make co-host?
Is iPhone?
Who is that?
Who is iPhone?
Yeah, it's not me. iPhone, it's not me. Just leave it there. We'll deal with that.
Remove co-host.
Okay.
Lorenzo is trustworthy.
Oh, so what is he supposed to do?
Admit people.
Right, so you
Oh yeah, Lorenzo, yes, let people in.
sitting down already.
Okay.
So, yeah. So I took this example from like a review paper on like automatic differentiation that become quite popular in machine learning. And so, yeah. So the goal here is basically we want to compute like the derivative with respect to one of the input x1, and we start with computing the derivatives of the intermediate variable. Reverse direction. Yeah, okay. So you can kind of make this graph like this, the computational graph. You have the inputs and then each operation is one intermediate variable. And finally, you have the output. All right. So let's just walk through how do we do these things. So on the left side is basically what's called the basic function evaluation. On the right side, you are evaluating the derivative. That's basically the thing. So what you're doing is that firstly, you are kind of seeding your inputs. So the first two variables, you want to compute the derivative with respect to one. So seed it with one, seed everything else with zero. In this case, it's a bivariate function. So the other element would be zero. And now just simply calculate the derivatives. So in each step, so you calculate first V1, which is like this node, right? So V1, V minus one, that's basically your input. And then the next node is just passed to V1. So yeah, you calculate that node and simultaneously calculate its gradient. And you just, you just go through that thing. And then finally, you get the output which you want is basically is all the intermediate variables derivative. But I would say like if you want to have a like look this, yeah. Okay.
Yes, so I just have a small question. So
Yeah.
if you want to change the value at which you evaluate the derivative, then you have to do the whole thing again.
Yeah, absolutely. Yeah. So it basically, like the best way to think of this as like taking the directional derivative. So you're taking the directional derivative at the point, let's say x, right? And now once you change the point or you move the point, so you again have to take the derivative. So that's the thing. So, but the thing is that the interesting thing here to note is that when you're designing an automatic differentiation library, basically, all you need to do is basically have your elementary functions, which can just take these, obviously it's function value, but then taking these derivatives along with them. So that way you evaluate the function and you're evaluating the derivative.
Yeah, can you say again why the first line of the forward tangent of the right hand side, why is that equal to 1?
Yeah, so basically if you look at x1, right? So you start with dx1, dx1, dx1. So you're taking,
Okay.
right? Because when you do the forward derivative or like the forward mode derivative, generally this is the important thing to remember, like each pass is taking the derivative with respect to one input.
So the rest, the other one, x2 is
Yeah,
assumed
so-
constant, so
yeah.
the derivative is.
Yeah, so if you want to take the derivative with respect to both, which we want, right? We want to take the derivative with respect to 1 and 2. So we need two passes,
Mhm.
right? Question, is this useful for statistics?
Yes.
So give you more context is like in statistics, what we have like n inputs, right? And at the end, at the top, we'll always have like a loss function, a maximum likelihood. Now, if we have a very high dimensional parameter space, let's say 1 million parameters, then we have to do this thing 1 million times. So naturally, this is very popular in certain communities, but in machine learning statistics, this forward mode is not that useful. But still, I mean, like this is very foundational, so I enlisted it here. This is one problem. Remember, like you need to sweep to your function as many times as your inputs are. And in statistics, always we have output smaller than input, right? Most of the times we'll have output as like a scalar and input as a very high dimensional vector. So that's not that useful, but yeah.
Big question. So then how do I know what is the dot derivative with respect to x1 or x2 in forward tangent derivative trace?
This is just like a notation chosen like in this paper. So like the basic point is like you choose dot for like basically this thing, like v dot is basically like the derivative of like whatever your intermediate value point is with respect to your actual independent variable that you want to derive.
The variable of interest at that stage. Right, okay, gotcha.
So variable of interest that stage by the actual input that you are concerned about. Okay. Okay. So what you can do is that if you take that initial tangent vector in a certain way, basically you take your initial tangent vector as like a unit vector with setting one input to 1 and setting every other input to 0. Then in each evaluation, you compute one column of the Jacobian. That you can do. So if you run forward mode AD, you run it one time, one single pass, you evaluate one column of your Jacobian. So if you want to, yeah. Oh, sorry. If you want to evaluate the full Jacobian, then obviously you need as many columns or you need as many sweeps as you have columns, basically. That's basically what. So now coming to reverse mode. And this reverse mode is kind of counterintuitive because this is not how we learn chain rule as, but this is actually what used predominantly. So the main thing here is we go back to the same computational. Remember that you are just doing differentiation. I remember it like that from left to right.
Another question. But is automatic differentiation then more expensive than computationally speaking than if you have the derivative and you just evaluate it? Or
I mean, like this is actually having the derivative and evaluative where you're having the derivative analytically. So automatic differentiation is doing everything analytically, right?
yeah. So computationally they have the same cost.
Yeah, same cost. Yeah.
Well,
But depending upon which mode you choose, the cost might vary.
so if you input the derivative that you have manually obtained,
No,
to
so
evaluate that.
so when you say of inputting the derivative manually obtained, do you mean like numerical derivative?
No, I mean you manually do derivation.
The analytical derivative.
Yeah. So one very like I would say charitable soul have to sit down and convert.
Yeah.
You take C++, let's say. Let's say you take C++. One very charitable soul has to sit down and kind of write all plus, minus, multiplication, all sort of operations as like having either forward or derivative mode added to it. And generally, obviously, good question. Why this automatic differentiation become super popular in, let's say, 2010s, 2012? Because all the big startups, Google, Facebook, PyTorch is Facebook software, and then TensorFlow is Google. They found machine learning to be profitable, and they put an army of people to kind of sit down and doing that work. Now, obviously, once you do that work, then you have something like TensorFlow or PyTorch, or there are a lot of AD libraries for C++ as well, and there are different ways to go about it. I don't want to go into that detail, but you can check out. So, for example, you can check out that paper, where it talks about implementation. There are different ways of, like, that's very hardcore software stuff, but yeah. So that's why their automatic differentiation picked up, because people, big, large corporations were channeling a lot of money in doing this, like, quite trivial thing is just write down new functions, all these things. But once you do that, then you have loads of benefits. Okay, so coming back to reverse mode. In the reverse mode, always we are concerned with this thing, which is like, for us statistician, this is the most important thing, is that derivative of the output with respect to all my intermediate variables. So here I am fixated on like my loss maxima or likelihood or posterior, anomalous posterior, whatever my output is. I want to differentiate it with some intermediate variable. And this quantity, dy dvi, it's called the adjoint. So basically what we do, you remember in the forward mode, we started from right and we moved to left. Here, we will just be doing it the other way. So we expand, like you take dy dv to dv1, then you expand, and remember, like, this thing, dy dv3 is basically 1. So here you seed with 1 on the output, and then you propagate to your input. So that's why it is called reverse mode. And because we are seeding from output, we are moving from output to input, the thing is that the important thing to note is that you need 2 passes. So I need 1 pass to go to the output to find the function value, and then I need a backward pass to come to the input and evaluate derivatives all through. This is why, if you study, I mean, like, if you know, like, in deep learning, you have heard this term called back propagation, right? This is the reason why it's called back propagation, right? Because you are starting from input, going through your whatever neural network or whatever your model is, generally, let's say a very complex composition of functions. You're starting from your input, going up till you reach the output, evaluate all the function values. Then you do what is known as back propagation and just go back. But obviously, that's how the term is used, came into popularity in machine learning. But generally, I think just reverse mode is more, I think, useful thing. Or you can think of this as like the action of the Jacobian on a cotangent vector, right? So this is what you do. In forward, you push forwarded your tangent from the input space to the output space to the action of the Jacobian. And you could do that sequentially. Here you can do it in the reverse way. You have a vector on the output space, and you want to take like the vector Jacobian product. So you can do it sequentially and push. Again, you have like a recursive relation. And again, obviously, if these are all complex functions, we don't care, because every time all we had to deal with just one vector Jacobian product, and we can do all this analytically. So even no matter how complex the function is, how big the inputs whatever the dimensionality of the input output space is, we can always write this analytically as a library and do it sequentially. And we do not need to form the matrix. So again, we'll walk through that example. And compute the adjoints. The adjoints is basically the derivative of your like output with respect to each of your intermediate variables. So here you start from the input, you go up to the output, and then from the output, you go back. Now, can you give it a try? I mean, like you can. So just think of this. You have your output in the graph, which is yeah. So you have your final node as like the output itself, and obviously d of the output by itself is 1. So that's why you seed it with 1. Just as in the forward mode, your first thing was basically input differentiated by input, so that was 1. Here it's output differentiated by output, so that's 1. Then that will give you the first adjoint, right? And now if you look at this, once you have your adjoint, then you can go in this way. So once you compute the adjoint, the first adjoint, you can use it to get the product here, and that becomes your second adjoint. So you have your V5, so that's your first adjoint. Now obviously you want dy d4, right? And then that expression will be this thing, your adjoint coming from the output. So basically here, think of, you have a function, each of your elementary function, you will be receiving 2 inputs. The first input will be the thing on which you want to calculate the function, and the other input would be the adjoint that's coming from top. And you just take the product of both to find that function's adjoint. And that way you can get the adjoints of all the different intermediate variables. I'll stop here like couple of minutes and like so that sinks in. Any questions?
Maybe I have a very stupid one. When you have a function like that, you can write the composition of functions in different ways.
Yeah.
Will that change the computational effort that you need?
Yeah, absolutely. So for example, you have to find the best way to kind of lay down the graph. That's like how you write the composition. Because let's say, for example, you have certain expressions or certain intermediate computation that you can already reduce, right? So you think of it in terms of compiler, right? When we write a code, I mean, like you can have a very bad compiler that will compile into a very lousy intermediate representation or machine language. Here, the same thing goes, that you can reduce the function a little bit by hand. So you have to write an intelligent compiler which will compile the graph. So for example, when people used to say that initially TensorFlow had a not really good compiler, so a lot of optimization needed for that. So that's a whole different business like game, where how do you compile these functions? But yeah, that's important point.
I have another question, probably more stupid. Why do we care about the derivative of with respect to y? Like at the end, like.
So think of y is like the likelihood. And we want to do maximum likelihood using some sort of gradient mechanism. So that's why we need the gradient of the likelihood with respect to its input. It's in dy dx. Where so
dy dx, I understand, but dy like something over dy, that's the thing.
You just do it to start the mechanism, right?
Yeah.
Not with the final goal.
Care about it.
Yeah.
No, you don't care about it.
At the top.
Yeah, you don't. It is kind of a seed.
Okay.
So you can think of this like you have like, if I go back to this, you're setting that as a unit vector, where only one of the element would be 1, which you need, and everything else would be 0. So that's basically what it is. So you just set that to 1. Any questions online?
So maybe I can ask a practical question. So
Yeah.
in my experience, so do you have anything later on the computational cost of the two?
Yeah.
So I'll ask you
I mean, like-
after you explain that because it's about that. So
So okay, moving on. So here, what reverse mode does is compute each row at a time. Like forward mode was computing each column of the Jacobian. Here it computes each row of the Jacobian. Now, and this is coming to your computational thing, is that if we have, let's say, as many as output we have, let's say we have 10 outputs and 2 inputs. This is not going to happen in statistics, by the way, thank God. But but I'm just talking about like in general, let's say you have 10 inputs and 10 outputs, 2 inputs. Then obviously this is more expensive because this reverse mode depends on the number of outputs. So the more number of outputs, the more sweep you need to do. So that is something you have to keep in mind. The other thing is that, remember in forward mode, you are evaluating both these things together, both the derivatives and the function value. Here you do your forward trace and then you do back propagate. But that means you have to save, and remember, see all these adjoints are getting multiplied. So basically you have to save all those adjoints. So you have a memory cost as well. So if you have a really big function, so for example, like think of like some sort of very big hierarchical model or very big graphical model, and you want to apply reverse mode. So there is a memory constraint, right? And there are intelligent ways to kind of implement that. So you have better memory. I got it. What is? Oh no, I am the culprit. Okay. So here you evaluate like one row at a time. So the number of outputs, the number of sweep. All right. So forward mode is more efficient when you have small input and very large output. We don't care about that. We'll never have that thing. But good to know if you come up with a crazy statistical formulation where you have like 100-dimensional output and 2 inputs. But then that's why I wanted to have this tutorial. Is basically like people think of automatic differentiation as reverse mode, but there is also this forward mode, and so you can have utility as well of forward mode. And obviously we love this second case where m is equal to 1. That's our loss function, likelihood, whatever, just a scalar, and that way reverse mode is more useful. So that's about it. That's all you have in automatic differentiation. So we'll begin, go back to the variational inference stuff, but like have like a break.
Just quickly, what are the basic examples you give for when you have large M, like many outputs?
Large M, mostly I think from there's some interpretation control that people give, but I am not that knowledgeable about the thing. Or the other thing, yeah. So the other thing is you can think, yeah, one other important example is that, if I can remember vaguely, is that if you want to calculate Hessian, right? Then you can form it in a way of like you take the forward mode and the reverse mode and combine both, because you need to combine, like you take the Jacobians in 2 different ways and then you combine those, the Jacobians take their outer product, I guess. So, and then you combine, get the Hessians. So if you want to build Hessians, which is like, you need Hessians for example, if you love to implement any of Mark Girolami's algorithms, or if you want to do all these, I would say, Newton type algorithms, right? So that way, actually, this becomes very useful. If you want to calculate Hessian using only reverse mode, then obviously you will be spending more computation. So that's one important example where we.
Sorry, I have another. It's more of my experience than a question. So forward mode, it's actually pretty efficient when you don't have a massive number of parameters. And in the language that I use, I mean that up until like 500 parameter is as quick as reverse mode.
Yeah, so it depends upon how do you implement forward mode. So the standard or the most popular way is something called dual numbers. I won't go much into detail, but yeah, that's some of the.
These TensorFlow, are they implemented in?
TensorFlow, I mean, like every month you go back to TensorFlow, there is something new. So I don't know, but like the PyTorch has now got a forward mode with dual numbers, like beta. JAX is basically another thing from Google that supports forward mode. Obviously, Julia has, I think, a very nice forward mode thing. But you will find a lot of old forward mode libraries back from the like late 90s, early 2000s, from, as I say, like different communities. For example, there's some in control. But I mean, like I've never played with it. But for the mainstream, I think PyTorch has already started forward mode. They might have got a beta release of forward mode. Google JAX has forward mode, and of course, if anybody loves Julia, then obviously Julia has everything. So, yeah.
But you decide which mode to use according to the dimensionality? Actually,
Now I guess now we have time to, or we have opportunity to think about that. When like back in like 2016, 17, when like, okay, I remember 2013, 14, I think that's when Theano came up. Theano was like the fast popular machine learning AD automatic differentiation library back in 2013, 14. And that time, like, yeah, it was a very sloppy library. It had forward mode, reverse mode, both. But generally people think of automatic differentiation as reverse mode. So that's why we wanted to have like a go about like a little bit of a forward mode. Now you have choice. So you take your problem, run both and see which one works. I mean, like unless you have like obviously in machine learning, you take like some of the smaller neural networks. So the small neural networks will be something like 50,000 parameters or 1 million parameters. So there is no question of, and if you take some of the large language model or these type of, they'll be having billion parameters. So there's no question of forward mode. But then I don't know how they manage the memory. For that you have to go into like because when you have, I mean, like there are techniques to do this memory management and all that, but then obviously these are software startups, so they have people to take care of that. But yeah, this is a choice you can think about, and one thing where you should think about, as I said, like taking Hessians if you want to do Hessians. But then there are other troubles of doing Hessians. So all right, so we can take like a break now and maybe less than 10 minutes if anyone wants to.
10 minutes.
10 minutes. We're stopping the recording.
Fair enough. I've seen you once at 7:30. He was very, very stressed.
Okay, so having introduced the automatic differentiation, previously I framed variational inference as a stochastic optimization problem. So basically the game is to kind of take a Monte Carlo estimate of the expectation, gradient of expectation, and then basically applies gradient descent, stochastic gradient descent. So obviously, let's consider like a classic problem, logistic regression. It's just like the simplest model you can have, but obviously you have problems. So if you want to do the classical VI, basically anywhere you put some sort of nonlinearity, nonlinear link function, or wherever you plug that type of things, you are out of luck. And so that's why you need to kind of go beyond the classical variation inference. Okay, so this is our elbow. And the lambda, if I'll remind you guys that the lambda is basically the variation parameters. And basically, we want to evaluate this quantity. That is, I write the cost function with f. And basically, we want to evaluate that one. Some sort of Monte Carlo trick. And that's basically the foundation of what we call modern variational inference. And obviously, as you can see, some of the references goes back quite a long way. But generally, most of the work, it's interesting to see that in the spate of like 2013, 14, there's a lot of work. And the reason is that that's when like the fast popular automatic differentiation library came out. So basically a lot depends on good engineering. I mean, like these ideas were there back in the 60s, forget about 90s. So, but obviously these people started applying them when they have like some of the tools available. So there's basically two ways to go about it. One is called the score function estimator, and the other one is called the pathwise estimator. And I hope some of you have heard this term called the reparameterization trick. So basically some technique or some way you reparameterize your variation. So let's look at the score function. Can you get rid of that?
Oh, I can do that. Yeah, so I'll do it. Sorry.
Sorry.
Yeah.
So this is the integral that we want to take, obviously. Now, the first thing to note in the first line is that we have done a trespassing. That is, we have interchanged integration with variation, right? And there are certain like conditions that you need on your function when you can do that. But let's say we take them for granted. Let's say we assume that those conditions are satisfied. And once we interchange the integration and differentiation, then we basically apply the log derivative trick on the Q, and we end up with kind of this expression. Right? So with these three lines, we have pushed the gradient inside the expectation, and this function, the derivative of a distribution with respect to its distributional parameters, is known as the score function. And once we have this expression, we can take, obviously, we plug back the plot function that is basically this one log and a log and just take Monte Carlo. So that's basically the score function estimate. So the trick goes is this one. It's a very, again, high school thing. Trick.
So the point is really to see the derivative as some expectation so that you can do Monte Carlo with it. Okay.
Yeah. And the question is how do we change limits and integral, right? Because derivative is limits, so we want to change limits and integral, right?
Can I ask another thing? Because when you work with this kind of expressions, I mean, for me it was in a different. For me it was adaptive MCMC, but you have the same kind of thing. So and it can be very relevant, the actual representation of the derivative, right? Because the variance of this derivative matters, right?
I'll come to that. Great question, I'll come to that. So let's look at the properties, okay? So obviously this is only unbiased when we can, this change of differentiation and integration is valid, and there are certain conditions which I won't go into. The only condition you should, I think it matters really because most of these assumptions, so basically you can prove that it's unbiased using applying dominated convergence theorem, and you need some assumptions, and one assumption, there is one sneaky assumption about absolute continuity. That means if your variational distribution is like a uniform, where your parameter is kind of, it's in its support. So its support is kind of based on parameter, then you have continuity problem. So yeah, so there is some theory there, but generally in machine learning application, I've said, because mostly it's used in machine learning, but these kind of. Now, obviously, your question, the variance of this estimate, it's pathetic, ridiculous. That's basically the one sentence or one word I can say. It's a big issue. Because if you just simply write down the variance, you'll first note that parameter dimensionality comes in. So obviously, if you have high dimensional problem, the variance grows larger. But then there is one other problem, is that your cost function also comes in, basically. So basically, if you again go back to that reverse mode automatic differentiation thing, is that you're taking the derivative of the score function. Now this gradient, right? If this is influenced by some of your variation in your function, so that will again kind of come and haunt your variance estimate. Generally, practically, basically impossible to use this score function estimator. And the whole research in this score function estimator is about basically how do you control the variance. And obviously, I'm just talking of, I'll just briefly touch upon the standard technique is control variates. So, I mean, like most of you must know what's control variance. So basically, you replace your original function of interest with this other function, and it's an unbiased estimate. And so if you just now write down the variance, turns out it basically you have an expression where you have like a reduced variance of this control variate based estimator, and that kind of, and then you can obviously try to figure out what is the optimal value for the coefficient, because you write the control variate like that, and you need to find the optimal value. Obviously, if you just do the math algebra and you'll get this expression, which basically implies that you choose this function, control variate function, which has high correlation of your function of interest. So basically that's based, I mean, like, this is not like variational inference totally basically in any control variates problem. So obviously one important thing I must say, that there has been there's a lot of research in applying control variates to MCMC, right? So you want MCMC chain, which is like having like variance issues, and so you will apply control variates. And then there's been development of these zero variance control variates, and all these a lot of kernel based methods in developing control variates. That research has not yet come here. So there's like still like lots of things people are looking at you can use. And the choice of control variate that people use is basically the score function, because it's obviously related or correlated, and because you have that property for the score function estimator. That's what people choose for the control variate. But then again, I mean, like, this is a standard statistical problem, right? And like, there's many different ways you might use, like, I mean, like, you can see people trying out all these things in tandem. Like, you do Rao-Black polarization, you do Cauchy-Monte Carlo and QMC, and then apply control variate. Somehow you kind of try to get on the variance thing that you said. And a lot of work happened on like those time period, 2014-15 on this, but then basically people gave up on this algorithm. There's still some application areas, but generally people moved on from this area. But still, this is a hot research topic, and obviously if you can reduce the variance a little bit, obviously that is a big contribution in this area. So that's an absolutely open research problem. Okay, so this algorithm, when you have variational inference using the score estimator, this is generally called black box variational inference. Why it's called black box variational inference? Because if you look into this thing, basically it doesn't, you just need a likelihood model or you need a probabilistic model where you can just evaluate the density, that's it. Now, obviously, some of you might ask, or people who are interested in SMC, that can I plug some sort of unbiased estimate? Maybe I cannot evaluate even the density. I might have like a state space model, but I can get an unbiased estimate of that. Yes, that will also work. Yeah. So basically you can plug in whatever you want as long as you have this density and or its unbiased estimate. And the important thing is that the derivative appears in the chosen distribution rather than your actual model. So that means you have like a, what I said, truly black box version. And the good thing is because you do not need to differentiate your log joint, that means it allows for discrete variables as well. So you can have discrete latent variables, or like some, if you have some categorical variable, then you can use that as well. And this implicit likelihood, by this I mean all sorts of like SMC, ABC, and all sorts of likelihood free methods where you can plug there some sort of distance function. So there's some work on that as well. So this is one area that this algorithm is quite useful in my opinion, because if we can figure out a way to control the variance, then this is a nice way to do ABC variational inference, right? So you do not need to run all sorts of very simulation intensive things. So variational inference will kind of squeeze down your simulations, and all you need is basically a good sort of control variant or some variance reduction technique, and you can use implicit likelihood models. But the problem is, in practice, variance stabilization doesn't really work that well. Right? So yes, yeah.
So for the stochastic Langevin diffusion, you need to tune the step size very carefully.
Come to that. But the difference is that in the SGLD, you remember, you still have to take, you need a differentiable probabilistic model, right? In that model. But here you do not need a differentiable probabilistic model. Yeah. So obviously, I can't remember if this is used in the context of MCMC, but yeah, I mean, like it is an interesting question. But on the other hand, is like, let's say you want to, because we are doing Monte Carlo here, so we can plug in any Q of our choice. So gone are like mean field and diagonal and all that. You can just use whatever you want as long as you can take gradient, right? So yeah, so if your Q can be like a Markov process, like you run an MCMC, question is how do you differentiate through the MCMC? Maybe you can do it in some way, like implicit differentiation or some sort of way. Then you can plug in like an actual MCMC trace here. Or, I mean, like as soon as you have these expression on Monte Carlo based gradient expectation, then you are free to do all these experiments basically. But in this overall framework of score function estimator, the main challenge is actually this variance stabilization, right? So that's the difficulty, and actually it's pretty hard, right? So this brings me to
Meeting control.
yeah. Okay, so that brings us to pathwise estimator. So this is the other technique of getting your Monte Carlo expectation. So obviously we know that if I have like a expectation, then we can kind of change the variable, right? So that's the Lotus application. So we just, rather than having the expectation with respect to Q, we change it to have an expectation with respect to some parameter free distribution, right? And in that way, we kind of reparameterize so that the parameter theta becomes output of some sort of invertible differentiable deterministic transformation. So I think Dev Roy kind of came up with this term one-liner. Obviously, the most famous and most popular is this one, right? So just we have like a one-line transform. And remember, this is basically what we know in statistics as non-centered parameterization. Basically, that's the trick. One thing to note is that
Stupid question. Why is it called the law of the unconscious statistician?
I don't know. Maybe anybody, if anybody has an answer.
I think it's because when you take it the expectation and you're like, I think usually when you're like an undergrad and you don't know how to do expectations very well, you would assume that you can take expectations that way, but then actually you need to prove it that you can do it. But I think that's why it's called that.
Okay. The interesting thing is that here you see that because you have changed the kind of variable, then all that's needed to do that limit and integration swap is now valid because you have changed kind of the underlying variable. And so as long as all of the functions are differentiable, right? If they are not discontinuous, then obviously the integration is valid. And so this is basically the reparameterization trick. The problem with this, I won't say problem, but limitation is that take, for example, gamma distribution. You have different ways to kind of, so you have to use rejection sampling, right? So that cannot be used. So you need densities that you can, and remember, I'm just giving example of one-liner, but there are other ways, like polar transform, for example. So there are different ways to reparameterize densities, but the function that you use to reparameterize G, so you generate the sample and you evaluate the density using the same path. So that's why the pathwise estimator. So not all distributions work. There are some work where you can kind of frame it in a different way, but this is the standard way. And obviously Gaussian is very popular because of that simple affine transformation, right? So basically, because now you have changed your integration with respect to theta to with respect to epsilon, so the limit goes inside your integration as long as f and g are differentiable. So no problem with that. And then just chain rule, you substitute back the actual function, then you get your what you want is your Monte Carlo expectation, and this is basically the samples are generated from a parameter free distribution. So for example, if I choose like a Gaussian, then obviously it's just a sample from basically the standard Gaussian, and then that's just it. So this has become like the default. What if somebody tells you like modern variational inference, this is this one equation, that's it. So all you need is a differentiable model. Here differentiability matters, right? But once you have a differentiable model, you choose your density, your variational approach, and you don't have to choose Gaussian, you can choose anything else, or you can choose a Gaussian and then transform. I'll talk about that later. But yeah, so that's where you get the Monte Carlo expectation, and then you can do the stochastic gradient descent. Obviously, and the variance now much more stabilized because you are doing all these reparameterization. Basically, what you're kind of trying to do is kind of suppress the effect of many random variables. So because now basically the only source of randomness is this epsilon from a parameter free distribution. So you're suppressing all other randomness. And so basically you become independent of the cost function because everything that's not affecting your actual gradient goes out, and so you have much more stable variance basically. And this is important, the stable variance, because now we can actually use it for any practical purpose, because the score function, you need to do control variables, route calculus, so many things, but now it just that one line and you get a stable variance, and now you can apply that. So that brings us to the last point. That's basically the automatic differentiation variation inference. So the setup, okay? I'm just going back to the simple probabilistic model. You have some parameters, you have some data, that's it. And we do not consider anything about the model except that it's differentiable. That's it, right? We do not consider conjugacy or anything. And now let's just start with back to our mean field. We're free to choose anything else, but let's just do simple mean field. And then the third ingredient is we are introducing a transformation function. So why I'm introducing this? So let's say I have a prior on theta that's basically gamma, right? And I want to use the Gaussian thing, right? So obviously immediately I'm back into trouble. So basically what we want to do is that we want to sample, or we want the variational approximation on the unconstrained real line, pass it through some transformation so that it goes back to like the constrained real line or the positive reals. And that's it basically. Important thing to note is that one example of this is the exponential function, right? And we use this type of transform almost all the time in MCMC. In MCMC, we do it in the other way. That is, we kind of change the priors so that, because in MCMC, we use like our proposal as Gaussian, our priors may be positive. So obviously we kind of change and then adjust for like the Jacobian, do the Jacobian adjustment. It's just the reverse way. So that once we have that, then basically this is the basic algorithm, right? So we start with our like iteration counter, step 1. These are our variational parameters. Initialize them, then sample parameter feed distribution, do the fast reparameterization using the G function. Then for those parameters whose support is constant, apply the T function, for example, an exponential. And then you apply basically the gradient of the elbow using that noisy elbow gradient. And then just apply stochastic gradient descent. And repeat until convergence. And obviously, as you can see, there are a few gradient calculations. So you have to take gradient with, you have to differentiate the G, you have to differentiate the T, and your model as well. So that's why automatic differentiation matters, right? So if you have to implement this by hand, you'll do it for one model, and maybe like if you're lazy like me, won't. And this algorithm was proposed in like by Alp in 2016. And if anybody uses Stan, then Stan provides this algorithm. So, yeah.
Sorry, I didn't understand the function T, the calligraphic T.
Oh. Okay. So think of like, the function is basically doing this thing. Like you want to have your variational distribution as a Gaussian, which is supported on the whole real line. Yeah. Now you want that function is just to simply transform it to kind of the positive reals.
Why? It's like a camera.
Because
the variable you're interested in is constrained.
Ah, okay. I see. Okay. So the tau.
I mean, like I can go back to MCMC. We do this all the time in MCMC. We just apply tau inverse in MCMC. That is, whenever when we are doing MCMC, whenever we have like a variable that is constant on the process.
Okay, I see.
We do a log, right?
Okay. Yeah.
Okay. So that, anyways, that
She muted.
Oh, it's done. Okay. So I mean, like, if you look at the algorithm, I mean, like, all you need is some differentiable function. That's basically it. And here I've chosen, I mean, like, we have chosen the best distribution, variational approximation, and Gaussian, but because of that T, it's the posterior is no more Gaussian. Right? So that's the important thing. So, like, here the actual posterior approximation is no longer Gaussian because of that transformation, and we can basically throw the kitchen sink at that T. Basically, I mean, like, you can throw a very complex T if you think for example, if you know that your posterior may lie on very twisted manifold, right, for which you use, let's say, some sort of manifold MCMC, then you can kind of throw a very complex nonlinear function that will take a Gaussian, transform it to a manifold, and then because you're using differentiation, then you differentiate everything. And in that case, you can have some parameterized T as well, and then club those parameters as part of your variational approach. So basically, you can go crazy here, basically. So how do you scale it to massive data set? Well, that's something that's very simple. You just basically kind of do what known as mini batching, right? And so that's a trick you can use for large data set. And Titius kind of came up with this term, doubly stochastic, because you have two sources of stochasticity. One source is coming from your data set, which is like if you have large data set, mini batch, and the other source is coming from your actual Monte Carlo gradient expectation. So now you have solution for both the problems we started this morning with non-conjugacy, data set.
Maybe
Bugs.
So
We want log P's.
yeah, log P. Sorry. It's the log there. Yeah.
after taking the gradient, then you want to converge to the minimum or maximum, whatever. Are you converging to?
That you will check in the practical. Generally, yes. Generally, you converge, but again, at the end of the day, this is a non-convex function. You're converging to a local minima.
Okay, so
Right. And so basically, I mean, like, there is nothing variational or Bayesian about optimization, right? I mean, like, people are thinking about optimizations in last 70, I would say 80 years, right? So obviously there is a whole lot of literature on how do, I mean, like, so let's take, for example, Levenberg-Markert algorithm, right? So people are have done lots of stuff. Like, I mean, like, this whole stochastic optimization thing, that came up in operation research, right? So from operation research, people brought it, Jeff Hinton and all the deep learning guys, they brought it, like machine learning. Now that has seeped into statistics. So I mean, like, there's really tons of theory there. For example, some people would treat that stochastic gradient, that equation, right? This equation as like a longeva diffusion, right? So you can start thinking of this as like a for the normal gradient. If we have like the full gradient, then that is basically an ODE, and then we can use Lyapunov functionals, general like nonlinear differential equation theory to look at whether it converges to a fixed point or not. For stochastic thing, obviously one way to look at this is through the lens of diffusion processes, and then you can study the stationary distribution and all that thing. There's a lot of theory. So stochastic optimization would be a masterclass in itself because there's so many.
So in practice, raw T, the step size you study.
Yeah, the step size. I mean, like every 6 months you will see a new paper of how this is the best way to do step sizes. So there is many different things people propose, because that step size is basically controlling how you're moving through.
It has to go to 0.
This step size, I mean, like, this depends on the condition, really, the Robbins-Monroe condition. So you have to have a bounded sequence. You have a decreasing bounded sequence basically. But in modern days, there's loads of different way people do that roti. Many of them are like, I found it and it works, and it works, and we don't know the theory why it works. Yeah, I mean, like talking about serious statisticians working on it, I think Michael Jordan's group is doing a lot of work on like looking at convergence properties. But as I said, I mean, like it's too big to cover. Yeah, it's a huge thing. Okay, so going beyond mean field approximation, we can basically, as I said, we do not no longer need the mean field thing, because all we need is differentiability. And if so, that's why these are some of the things people use. There's many more things, but the structured mean field came long back actually. It's basically, rather than having like a factorize, so if you have 10 components, you do a factorized distribution. Don't do that. You use some sort of hierarchical model, introduce some sort of dependency structure. Autoregressive, clearly, obviously, if you, for example, let's say you have a time series model, right? So obviously, good approximation would be, let's say, an AR2 process or a AR1 process, right? So you can use those. The last one is actually, this one is quite interesting because it looks like the most simple approximation, but actually, in my opinion, I have used this a lot. Actually, it kind of gives you almost indistinguishable results to MCMC. Yeah, I mean, like if you have 50 parameters, I mean, like inverting that covariance is not that difficult, right? And so you take a full rank Gaussian, pass it through some sort of transformation, even simple elementary like exponential transformation. I mean, like at up to 50 parameters, you get same results as MCMC. I mean, nothing can be easier, right? So if we go back to yesterday, I mean, like pages of derivation, obviously that's fun in itself. I'm not going into that, but like apart from the fun, if you are into real business, right, like you want to develop some products or something, or you want to apply variational inference to a new problem or something, you have to go and do all this derivation manually. And obviously, one of the famous example is, I think, a topic model where like it was a big probabilistic model. It was published, and later, like years later, people figured out that there were some algebra issues, and it still works. Actually, it's so you have all these troubles, but now basically all this is free form, right?
Can I ask also a question? You said the last one, it works well. So if you have a bimodal, okay.
Talking about bimodal, I will have one more, I think, session on generative models, normalizing flows. Rob will talk about that. Then my bimodal thing is also not problem. So for example, I mean, like obviously you, rather than that, you can take like a kind of a mixture.
But if you don't know how many components you have, can you also do that?
I mean, like you. So for example, see this where this thing is a lower bound to the marginal life. Obviously, a lower. You should not use lower bound for model selection, but for just testing out theory or like just testing out, take your like mixture of Gaussian, fit with this, find out the maximum elbow value, then think of these as like a marginal likelihood, and then you're in a domain of like base factors or like so you can do model selection. Please don't take my word for that. It's banned to use elbow for model selection, but nobody heard me. You can do it. It works. Yeah. Okay. So some practical tips. Yeah. Obviously, this is analytically. I mean, like if you're using Gaussian, obviously, because in ADVI we use a Gaussian and then transform it. This expectation is you can do it analytically, right? It's the entropy. And something that I not mentioned in the algorithm is that generally we do not do that. We take log of sigma because of it. But yeah, so and if you're using the full rank, then use a log-Koleski kind of parameterization where you take the diagonal elements. First you take the, basically if you're using full rank, then your parameter is the Koleski. Where, right, your Koleski so you do the factorization, so then that's basically your parameter, and then you take like log on the diagonal, so that way you better performance. Generally initialize things with small value, and
I had a question about the curly T thing. Like, essentially, you just use it to match the support of the normal to the support of,
that's it.
That's it. There's nothing more.
Nothing more, but this is the thing I'm saying, that the original idea of doing that was like just match the support, but actually that kind of gives a lot of extra niceties. I mean, as I said, like generally a lot of problems where we need a manifold MCMC because my posterior is blah blah blah. Basically, you just do a Gaussian and then put an exponential, and generally you do actually very close. That's my practical advice and my experience.
I think one of the things Stan did pretty early on was just say when you put a variable in the model, you say what its support is, and then they just have automatic options for the transformation, so you don't think about it. So it's really automatic.
Absolutely, and I mean, like, so all probabilistic programming libraries now support that. I mean, like, we do that all the time, but we do it on the other way. Like we transform the positive real to the unconstrained real, like when we are doing MCMC, like all of you, when you are implementing your MCMC code, you have done it, right? Obviously, there are serious other bigger problems where it might not work, but a lot of problems it actually works quite well. So avoiding gradient descent. So, okay. So coming back to your point. Okay. So if we have this sort of contour function of our cost, right? If we do, we know this is basically what is called ravines, right? And so if you use the vanilla stochastic gradient descent with just a standard decreasing step size, you will oscillate in that ravine. So one earlier suggestion, like which is used a lot, is momentum. So think of this is like, you know, when you're sloping, when you're pushing a ball down the slope, if you know that's the right direction, then you should apply it picks up momentum and goes faster. So it's kind of putting momentum in this horizontal direction. And one way to do it is basically kind of take a fraction of the update vector from your past time step and apply that. So just change this a little bit. So that this just change the vanilla gradient, stochastic gradient with this momentum thing just a little bit. And there are many other techniques of how do you do the momentum. I mean, like, it's a glossary of things, but the basic idea is very simple, is that if I want to go in this direction, I better have momentum in this direction. That's basically the idea. Obviously, the next thing that pops out is that obviously if I want to go in this direction, and I don't really want to go in that direction, and I have a bivariate parameter, then rather than having like a fixed row value for both direction, I should have different step size values for different. So you have to adapt your step size according to your coordinate. So whichever
a matrix pre-multiplication of this.
Yes, and all sorts of modern, like you see AdaGrad, Adam, RMS prob is basically that idea. You multiply a matrix to the kind of your learning rate so that it kind of orients according to the eigenvector direction on that. Correct. That's it basically. There's not. So obviously, as I said, every 3 months you will have a new stochastic gradient on, like, a little bit of this little, but basically these two are the main idea. And apply momentum, adapt according to the coordinate space where you should go. That's basically it. Okay, to summarize, yeah, it's not truly black box. So for example, if I have a ABC problem, then I don't know, I mean, like, this is not useful. The score function, if you can manage the variance, it will be more useful. And obviously, upfront, it does not support discrete latent variables, but there are tricks like the Gumbel softmax trick or the basically reparameterization of a categorical variable. So there have been like some papers on that. You want to differentiate through a categorical variable because you have your latent variable which is discrete, and obviously you cannot differentiate. So some way to kind of have a continuous reparameterization or continuous approximation to a discrete distribution. That's basically the idea. So that makes you apply this thing. And the biggest and most important thing is you have like a much more stable variance. And yeah, and this is like anytime you hear Bayesian neural network, Bayesian deep learning, Bayesian blah, blah, blah in machine learning, this is basically the engine that's running behind it because it allows you to put the kitchen sink there. So obviously, you're no longer in like diagonal mean field and all that. But obviously, even if you have mean field, you can, I mean, like, obviously, it's up to you. You can use mean field, you can use full rank Gaussian, you can use, yeah. Okay. Okay, so coming to the practicals, there will be just two practicals. Both will be applying the ADVI algorithm, and one will be just a simple linear regression, and the other will be a logistic, all with simulated data. And this will walk you through applying this kind of thing. So I'll share the GitHub repo, and the thing is that I hope everybody has a Gmail account, right? So
Drive. Because it's Google Drive.
no, it's not Google Drive. It will be run on the Google Colab framework. So you don't need to install anything. You just open this thing and a web page will open, and there you can run everything. You don't need to install and do anything.
Can you also put the slides up?
Yeah, obviously, I'll do that.
Stop
the record. Yeah, I just want to open the